Lastly, let's talk what exactly goes on in heat engine cycles. In this diagram, it shows the basic process of a steam power plant, which is a common heat engine. We have the boiler for heat input, the turbine for work output, the condenser for heat rejection, and pump for work input. First, it goes through the boiler. Fuel and air are burned into the boiler, producing high temperature gases. These gases transfer heat to water inside the boiler, turning it into high pressure, high temperature steam. The steam now contains the thermal energy needed to drive the turbine. The exhaust gases are released after combustion, while the steam moves forward into the turbine. Next, we have the turbine for work output. The pressurized steam enters the turbine and expands. As it expands, it pushes against the turbine blades, causing them to spin. This spinning motion produces mechanical work, which is often connected to a generator to produce electricity. The steam exits the turbine at a much lower pressure and temperature, having given up much of its energy to produce useful work. Then we have the condenser for heat rejection. The low pressure steam enters the condenser. Cooling water from a river, cooling tower, or other source absorbs heat from the steam. The steam loses energy and condenses back into liquid water. This step is essential because not all heat can be turned into work. Waste heat must be rejected, as dictated by the second law of thermodynamics. Lastly, it goes through the pump for the work input. The liquid water from the condenser is not yet ready for use because it is at low pressure. A pump increases its pressure, preparing it to re-enter the boiler. This requires some energy, but the work needed by the pump is small compared to the work produced by the turbine. The high pressure liquid is then fed back into the boiler, completing the cycle. This process operates in a continuous cycle, often referred to as a closed loop. It keeps running as long as two essential conditions are met: a steady supply of fuel to sustain combustion, and an effective cooling system to remove the excess heat that cannot be converted into work. By maintaining this balance of heat input and heat rejection, the engine is able to convert the energy stored in the fuel into thermal energy, then into mechanical energy. In many modern systems, this mechanical energy is further transformed into electrical power through generators. This sequence highlights the efficiency and importance of the heat engine cycle, showing how it enables continuous energy conversion as long as both the fuel and cooling requirements are consistently supplied. To sum it all up, heat engines, whether internal or external, are machines that convert heat energy into mechanical work. They may differ in how fuel is burned and how energy is transferred, but both play an important role in transportation, power generation, and everyday life. So that concludes my report on heat engines, and now I'll hand it over to the next reporter.
Good day everyone. Today I will explain about the Stirling engine. What is a Stirling engine? A Stirling engine is a power system that uses compressible gases in a closed cycle. This means the gas doesn't escape. It just keeps moving around inside the engine. It is called an external combustion engine because the fuel or heat source burns outside the engine, unlike a car engine where the fuel burns inside. The heat from outside makes the gas expand and contract, and this movement is used to create a mechanical work. A Stirling engine was invented by Robert Stirling in 1816. It was designed as a safer and more efficient alternative to steam engines at that time. For example, instead of using gasoline like a car engine, a Stirling engine can run using solar heat, burning wood, or even waste heat from factories, and that makes it very flexible. Even though it can be more efficient than gasoline or diesel engines, today it is mostly used in special applications. For example, in submarines, because it runs very quietly, and also in yacht as an auxiliary power generator. Now that we know what a Stirling engine is, let's talk about how it actually works, or the working principle of a Stirling engine. So the first one is, when the gas is heated, it expands, right? And pushes the piston forward. The second one is when the gas is cold, it contracts, and then the piston moves back. For the third one is, this repeating cycle of expansion and contraction produces continuous mechanical work. Example of this is, think of it like blowing air into a balloon. Diba, when you heat the air inside, the balloon expands. And when the air cools, it shrinks back. In the Stirling engine, this expansion and shrinking of gas is used to push and pull pistons, which then create a useful power, as you can see on the picture. Most importantly, this often uses a regenerator to save energy. For a Stirling engine to work, it needs three important things, and we have three essential parts of a Stirling engine. The first one is heat source. This can be a fuel burner, a solar collector, or even heat from a fire. The second one is working gas, usually air, helium, or hydrogen, which expands when heated and contracts when cooled. The third one is heat sink, a cooling system like air, water, or fins that removes heat so the gas can contract again. For example, a Stirling engine can use the sun's heat with a solar dish to generate electricity. It can also use to waste heat from factories or even from a simple wood fire in small engines. Next, we'll look at the types of Stirling engines, generally classified in two main ways: mechanism and configuration. First, let's talk about the mechanism. The first one in that is kinematic Stirling engine. This uses a crankshaft and pistons, similar to the engine in a car. When the pistons move, the crankshaft turns, which produces motion. Example, some Stirling engine uses a small boats or model engine are kinematic because they need to steady mechanical movement to turn wheels or propellers. The second one is free piston Stirling engines. This has no crankshaft and it has linear alternators. Instead of turning wheels, their motion is used to generate electricity through a linear alternator. Example for that is NASA has tested free piston Stirling engines in space projects to generate electricity from heat because they are quiet and relatable. Next is the configuration, and it has three types: alpha, beta, and gamma type. The first one is alpha type, and it has two pistons, hot and cold. And the second one is beta type. It has one cylinder, a displacer pistons that moves the gas around, and a power pistons that creates the actual work. And the third one is gamma type. It has a displacer and a power piston, but it has a separate cylinder. To wrap it up, by mechanism, the kinematic is like a car engine with a crankshaft, while pre-piston makes electricity directly. And by configuration, alpha has two pistons, hot and cold, beta type has only one cylinder, and gamma type has separate cylinder. Each type has its own strength, and that's why Stirling engines are used in different ways. Now that we know the types of Stirling engines, let's look at how the Stirling cycle works, and this diagram shows the process step by step. The first one is heating and expansion. the gas inside gets hot, expands, and pushes the piston down to produce work. Example ani is like heating air in a balloon. It swells and pushes outward. For the second one is flow and cooling. The piston moves up and pushes the hot gas into the cold cylinder. There, the gas cools down, shrinks, and lowers the pressure. Example like a hot balloon left outside in the cold and it shrinks. The third one is compression. The cooled gas is compressed by the piston. Since it's cooler, it takes less energy to compress. And the fourth one is reverse flow and heating. The compressed gas flows back into the hot side. It heats up again, expands, and the cycle repeats. You can see on the slide, figure 2, basic ideal Stirling cycle. The diagram shows how it works and how it is. The gas is heated and expands to push the piston, then cooled to lower pressure, and then compressed with less energy, and finally reheated to repeat the cycle. This continuous process turns heat into mechanical work, and the heat turns into smooth that can power machines or generate electricity. And this last slide shows the references we use in our report. That's the end of our presentation with my groupmate Alexa Fabekirol and me, Bernadette Mabel Pipakinol. Thank you all for listening. We hope you learned something new about heat engines and Stirling engines.